The 1960s. The world watched rockets on black and white televisions. Millions followed every launch. Space fever gripped the entire planet. But some engineers looked down, not up. Not to the stars. To the ocean floor. What if humanity's true future was underwater? Between 1960 and 1969, visionary architects sketched an entirely different world. Subaquatic luxury resorts. Underwater hotels. None of them were ever built. Designers targeted clear tropical waters. The Red Sea, the Caribbean. Why go under the surface at all? Growing populations needed new living space. Firms like Donald Deskey Associates designed submerged lounges and coral view suites. They promised total immersion among coral reefs, just steps from your bed. But how would humans survive under crushing water pressure? Engineers proposed spherical structures. Round shapes resist pressure better than flat ones. Curved acrylic windows would replace flat glass panes entirely. Guests would descend through pressurized shafts or ride personal submersible capsules. Electric shuttles would ferry visitors straight from surface ships into submerged lobbies.
À Luxury Suite, tirti-meté underwater.
That was the actual pitch. And yet, every single commercial project collapsed before construction ever began. Saltwater corrosion destroyed 1960s materials fast. Costs spiraled far beyond reach. Governments poured billions into the Cold War space race instead. Insurance underwriters refused to cover a catastrophic pressure hull failure. No insurer would risk civilian lives inside a leaking habitat. Fresh air alone required complex, expensive life support machinery around the clock. Operating costs simply outpaced what any nightly room rate could recover. Was this dream just decades ahead of its actual technology? These failed concepts still mattered enormously for modern marine engineering. They proved humans could adapt psychologically to living underwater. The commercial dream failed completely. This technical legacy never did. In 1962, French oceanographer Jacques Cousteau launched Conshelf. His mission: prove humans could live underwater permanently. Conshelf, I placed 2 divers 10 meters deep off Marseilles. They lived inside a steel cylinder for 7 straight days. It worked. So in 1963, Cousteau went further. Conshelf 2, deep in the Red Sea. An entire submerged village. 5 aquanauts lived there for 30 days. Their starfish-shaped main house held living quarters, labs, even an underwater garage. A small submarine docked directly inside the structure itself. Aquanauts cooked real meals, played chess, drank wine while watching fish outside. A second, deeper cabin sat 30 meters down, testing heliox gas. 2 men stayed there a full week, breathing helium and oxygen in total darkness. Then, in 1965, came Conshelf 3, off Cap Ferret, 100 meters deep. 6 men lived inside a massive steel sphere under extreme pressure. Dense helium turned their voices into high-pitched squeaks. They performed genuine maintenance work on a simulated oil wellhead. Cousteau had proven it. Saturation diving worked for weeks at a time. Yet commercial investors still hesitated. Research was one thing. Tourism was another entirely. While Cousteau pursued science, the U.S. Navy pursued military dominance underwater. In 1964, Sealab I dropped off Bermuda's coast, 60 meters down. 4 aquanauts lived inside a pressurized steel cylinder for 11 days. Saturation diving prevented decompression sickness entirely, a major breakthrough. But dense helium raised their voices into comical, almost unintelligible squeaks. Commanders needed electronic speech unscramblers just to communicate during emergencies. In 1965, Sealab 2 sank off La Jolla, California, 63 meters deep. Former astronaut Scott Carpenter led the team through 40 grueling days. A trained dolphin named Tuffy ferried tools and mail to the crew. Divers battled icy water, near-zero visibility, and constant equipment failure. High humidity caused electrical shorts and painful skin rashes throughout the mission. Still, Sealab 2 proved seafloor bases could actually work operationally. Then tragedy struck. 1969, Sealab 3, off San Clemente, 182 meters down. A helium leak occurred while securing the habitat structure. A missing scrubber canister let carbon dioxide build to lethal levels. Diver Barry Cannon died from CO2 poisoning. The Navy suspended everything immediately. Sealab left behind priceless physiological data and real engineering breakthroughs. But it also left behind fear. Investors watched military divers die underwater. Commercial confidence in permanent seafloor habitats collapsed almost overnight. Every 10 meters deeper, water pressure climbs relentlessly. Flat structural glass shatters instantly under this crushing force. Engineers needed an entirely different approach to transparent materials. Throughout the 1960s, labs tested thick acrylic plastic formulations. Acrylic offered better flexibility and impact resistance than ordinary glass. Hydraulic pressure chambers pushed experimental viewports to their absolute breaking point. The results were clear. Window shape mattered more than raw thickness. Spherical and conical viewports spread external forces evenly across their surface. Flat acrylic sheets buckled fast. Curved domes actually grew stronger under load. So engineers built double-walled acrylic hemispheres, locked inside heavy steel retaining rings. Flexible rubber gaskets sealed every metal seam against subtle structural shifts. Saltwater brought its own destructive threat to structural metal hulls. Ordinary steel corroded at alarming rates once submerged for months. Microscopic pitting weakened heavy, load-bearing frames surprisingly fast. Metallurgists turned to nickel-chromium alloys and specialized titanium coatings instead. These materials resisted galvanic corrosion well, but came at exotic, military-grade prices. One final threat lurked, quietly: material fatigue. Repeated pressurization cycles caused microscopic cracks around every window joint. These invisible fractures spread silently, expanding under continuous ocean wave motion. A sudden collapse could destroy an entire habitat in seconds. Safety margins demanded impossibly thick walls for anything larger than a small room. Keeping human beings alive underwater required incredibly complex environmental control engineering. Submerged habitats functioned as completely closed ecological systems beneath the sea. Engineers needed to maintain safe, breathable air mixtures continuously for months. Oxygen levels had to stay precisely balanced to prevent hyperoxia or hypoxia. How could technicians recycle air safely inside a sealed steel vessel? Carbon dioxide scrubbers formed the most critical line of defense. Exhaled carbon dioxide accumulates rapidly in enclosed spaces without constant filtration. Early habitats utilized chemical canisters packed with soda lime or lithium hydroxide. These chemicals absorbed lethal carbon dioxide gas before it reached toxic concentrations. A single scrubber failure could cause unconsciousness or death within minutes. Would emergency air systems react fast enough during sudden mechanical failures? Humidity control presented another massive engineering nightmare inside submerged structures. Cold ocean water surrounded the thin steel walls of every habitat. Internal warm air condensed continuously against cold metal surfaces like rain. Moisture soaked electrical wiring, causing constant short circuits and severe mold growth. Aquanauts lived in perpetually damp environments that caused painful skin infections. Could commercial hotels ever provide luxury comfort in such humid conditions? Thermal management required massive amounts of electrical power sent from surface support ships. Deep-sea water kept internal habitat temperatures freezing cold without continuous artificial heating. Furthermore, helium gas used in deep-breathing mixtures conducted heat 6 times faster than air. Aquanauts lost body heat rapidly, shivering constantly even inside heavy neoprene suits. Electric heaters worked endlessly to keep internal living quarters marginally livable. What happened if a storm severed power cables from the surface ship? Emergency backup systems had to operate flawlessly during sudden power losses. Engineers designed heavy lead-acid battery banks sealed in pressurized exterior pods. These emergency batteries powered essential life support systems for up to 72 hours. Scrubbers and basic lighting remained operational while surface crews organized rescue efforts. However, long-term survival depended entirely on unbroken logistical support from the surface. Could private hotel operators guarantee absolute safety during unpredictable ocean storms? By the late 1970s, the underwater dream was already fading. Then came the global oil crisis. Priorities shifted hard and fast. Investors abandoned high-risk ocean habitats. Insurance costs proved simply impossible. Governments redirected funding toward offshore drilling and military submarines instead. By the early 1980s, civilian underwater hotels were shelved for good. Blueprints once promising coral reef suites faded into forgotten archives. The space race won every headline. The ocean race lost its funding. Still, its engineering legacy quietly shaped the deep-sea technology we use today.